hydrogen side. So we will be very sensitive to donated hydrogen bonds, but insensitive to what happens on the back of the molecule in accepted hydrogen bonds. It's a very high, it's of the order of 540 electron volts. So it's a highly excited state, which means that it has a short lifetime. Then we get a decay. The dominating channel is, of course, Auger decay. But a minority channel is fluorescence. Then we get an X-ray photon out that can be detected. That gives us a direct measurement of the energy difference between the valence states and the core level. Here's what we see then. So this is gas phase of water. Now, when we remove the 1s electron, we basically make oxygen into fluorine, because we remove one screening charge. For the occupied, the bonding levels, 1b2 and 3a1, there would be large vibrational excitations, because FH2 plus is not happy in the geometry of H2O. So we get Frank Condon broadening and they become smeared out. But the lone pair, the non-bonding lone pair, remains very sharp. And in the liquid, we get two sharp peaks, which I will come back to. So, X-ray absorption. When we did this for Anders, it's a difficult experiment, and Anders was the first one to be able to measure at the oxygen kh of liquid water. We were not interested in water. We wanted to look at biomolecules in water. But in order to see the biomolecules, we had to have a background spectrum of water to subtract. But that background spectrum did not look as it should. And what would one expect from a tetrahedral model of water? Well, it should be similar to ice. Ice is very tetrahedral. Okay? Now, we get a sharp conduction band in ice because the distances are well defined. There are similar distances. And since we excite into unoccupied states, the position of the anti-bonding orbitals depends on the distance between molecules. So if we have more disorder, if water is like ice, tetrahedral but more disordered, we would expect a smeared out light spectrum. Many different distances, many different energy positions. That was not what we saw at all. This is the X-ray absorption spectrum of liquid water. This is the spectrum of ice. So they're very different. So in the liquid, we lose basically the tetrahedral signal that we see in ice. We get a new sharp feature here that we call the pre-edge. And we get this main edge, which becomes very strong. This is ambient temperature, room temperature. But here's a comparison between 4 degrees and 90 degrees. So the differences are small. Now, what we see is what we would expect from this difference. That when we heat the liquid, we lose intensity in this region, which we call the post edge. And that's the region that is strong in ice. And instead, we gain intensity in the pre-edge and the main edge. So intuitively, we would associate the pre-edge and the main edge with breaking hydrogen bonds. Now, what we did was to do a lot of MD simulations of water. We took out different structures and calculated the X-ray absorption spectra. And this is what we find. If we take the structure of ice, we have a good representation. If we look at, from the simulations in the liquid, take out molecules that have 4 hydrogen bonds, we get something that looks like ice. if we break an accepted hydrogen bond on the backside of the molecule, it still looks like ice. But if we break one of the donated hydrogen bonds, making the hydrogen bonding asymmetric, then we lose intensity here, we gain it at the pre-edge, we gain at the main edge. So this is a theoretical prediction. But then Anders could go back to surface science and on a platinum substrate build a film of ice. Ordered, overlaid. Here we have an extreme asymmetric situation. One donated and one hydrogen pointing to vacuum. Looking with the X-rays straight down, you basically only see bulk water, tetrahedrally coordinated. And you get a spectrum like this. Looking grazing along the surface, you mainly see these molecules, and you have a spectrum like this. Very strong pre-edge, almost no post-edge. To make sure that we only look at these and not defects inside the ice, we can put down just a monolayer of ammonia, and that quenches these free OHs, and you get an ice-like spectrum. So we have a good assignment of the pre-edge and the post-edge. Now what about the main edge? Well, the main edge turns out to be very sensitive to the packing or the density in the local density of the molecules. So these are now spectra of different ices. Now going from hexagonal ice with a density of 0.9 grams per cubic centimeter all the way up to ice 8 at 1.6 grams per cubic centimeter. And what we can see is that we have a shift in the ratio between post-edge and main edge, where the main edge grows more and more. This can be correlated to the second shell distance in the paired correlation function. And it's a linear relationship. So here we have the main edge to post-edge ratio. Here we have the second shell distance, and they all line up. Similarly, we can correlate to the density. But then the liquid falls off the curve. And this is an indication that in the case of the liquid, we might actually have a heterogeneity. That the main edge to post edge are determined, that the second shell distance is determined by one component in the liquid. And this will be the low density liquid, which has a very structured pair correlation function, while the high density-like component has a very flat pair correlation function, does not contribute to the second shell. Okay? Here's X-ray emission spectroscopy now. So on the left we have the full spectra. Here we have gas phase. Here we have crystalline ice, and we can see there's a shift between gas phase and the condensed phase. Now, in the liquid, we get a split with one peak close to the gas phase and the other peak close to the position in tetrahedral ice. We have a sequence of different temperatures, and we can see that when we heat the liquid, the peak here, which is close to the tetrahedral position, goes down in intensity, and instead the other one rose in intensity. Here we zoom in to just this region. And what we can see is that this peak that we will call tetrahedral stays at a fixed energy position and decreases in intensity, while the other one increases in intensity when we heat the liquid, and it also shifts towards the gas phase, which means that somehow it gets thermally excited, and the hydrogen bond network becomes more and more weakened and approaching non-hydrogen bonded like gas phase. Okay? We don't see any broadening. There are no new features coming up. So it's just a conversion of intensity from this to that, and a thermal excitation of this component. We can connect the two spectroscopies because X-ray emission comes after the absorption, which means that we can use the photon energy to select where on the liquid spectrum we do the excitation. We need a reference, and the reference will be at 550 eV, where there's no structural sensitivity. The reference is this black line here. We can see if we excite at the post edge here, we excite where we have growing intensity when we cool the liquid, and we get a higher signal of the peak, which grows when we cool the liquid. So they are connected. When we excite at the pre-edge, which in the science paper we assign to uniquely asymmetric hydrogen bond situations, we only get one peak. So we can select which type of local structure in the liquid that we want to measure. Just a summary, we assign tetrahedral structures as a minority at ambient conditions, distorted structures with only one donated hydrogen bond, the other basically free, as a dominating contribution at ambient temperatures. We interpret this in terms of a competition between enthalpy and entropy. So this is very much similar to what Professor Anisimov discussed before. And we see this now in the experiment. We convert from this type of structure over to this. This does not get thermally excited. This one gets thermally excited. So we can assume that this new or other component can contribute to the entropy at higher temperatures. We see similar behavior in the pre-edge and main edge in X-ray absorption, that they shift towards the gas phase. The way we interpret this is in terms of the librational excitations in the liquid. Now, if you are tetrahedrally hydrogen bonded, the molecules try to rotate, but they rotate against 4 hydrogen bonds, which makes a very sharp potential, which then, when we quantize, gives large steps. So the steps, the frequency, the libration modes in ice are around 800 wave numbers, which is like 3 to 4 times kT at room temperature. So they will not be thermally accessible. They will not contribute to the entropy. If we break hydrogen bonds, the molecules become freer to rotate. The potential energy surface comes down, becomes flatter, the level spacing comes down, and we can now thermally populate these levels. And there we have a contribution to the entropy. Okay, so small angle X-ray scattering. So this is now done with X-rays. We have very short wavelengths. But by going to very small angles, we trick the light to see correlations even at very long distances. I will assume that you're familiar with small angle neutron scattering or X-ray scattering. Basically what we will see here are density inhomogeneities in the liquid, and we can extract also the length scale of them. On the left here we have a normal liquid, the temperature-dependent small angle X-ray scattering of ethanol, normal alcohol. What we can see is that as we cool the liquid, we just have progressively less and less scattering as the thermal disorder in the liquid becomes less and less. Now, for water, on the other hand, here we go from room temperature, 284 Kelvin, it's a cold room. And as we cool the liquid down to minus 21 degrees C, we see an enhancement of the scattering at low Q transfer. This is connected to the isothermal compressibility. And this has been extracted from sound measurements, sound velocity measurements in the liquid. And that's the dashed line. And the red and black curves here is what we extract from the small angle X-ray scattering. So we have a very good fit to that data. We can also, from the anomalous component, extract a correlation length through the Ornstein-Zernicke relation. And I will come back to that at the end of the talk, because that was requested before. Now, what about simulations? Well, if we want to simulate a small angle X-ray scattering going to small q, we have to have a very big box, because we're going to take the Fourier transform of the atom positions in the box. We also, so we use 45,000 molecules here. We also need a force field that can actually reproduce the isothermal compressibility reasonably well. The TIP4P 2005 model actually has a reasonable, it's the best model actually for the thermodynamical properties. So we do these simulations, and here we compare directly with experiments. So at 5 degrees, we have a perfect match in terms of the shape of our computed SACS data. However, we do have to shift the curve a little bit to match the match quantitatively. When we start to supercool, so here experiment going down to 263 Kelvin, then in the simulation we have to cool down to 253 Kelvin. So we have to cool down more. Going even further down to 258 Kelvin, we have to go down almost 20 degrees more to have the same type of fluctuations. And when we are at 252 Kelvin experimentally, we have to go down to 230 Kelvin, and we still underestimate the fluctuations in real water. And here at 230 Kelvin, this is the maximum in this model. We are at the Widom line of the model. This has been discussed very much, so I'm not going to say too much about it. But the Widom line is the extension here. This would be the picture that we also arrive at based on the experiments and the combination with simulations. So that there actually is a critical point in a liquid-liquid transition between a high-density liquid and a low-density liquid. The fluctuations that we see at ambient conditions, biological conditions, would be due to the vicinity of the Widom line and the critical point here. But in order to experimentally say something about this, we need to go deeper in temperature. Here's a comparison now of the isothermal compressibility. Now, it has been measured for real water down to about 250 Kelvin about. When we look at the simulations here, this is TIP4P 2005. We underestimate the fluctuations. Here we hit the Willem line at 230 Kelvin. And after that the fluctuations decrease, and they decrease because it becomes more and more dominated by the other component, the low density liquid. Now, if we take another model, the SPCE, it has a much flatter maximum down here. So here's the Willem line at ambient pressure for SPCE water. Now, the enhancement will depend on the vicinity of the critical point. How far away, at the critical point, we would have a strict divergence. Now, the critical point for TIP4P 2005 water is at 1.35 kilobar, but for SPCE it's at 2.9 kilobar. So we have a much smaller enhancement for SPCE, much bigger for TIP4P 2005. But where will it be for liquid water? Do we have a divergence, or will it bend down? In order to see that experimentally, we need to go into no man's land. And the way to do that is the reason that one has not been able to do experiments in no man's land is that the measurements take too long. The water crystallizes before the measurement is over. So you need a fast measurement technique. What we have used is the X-ray laser at SLAC at Stanford. This is the first X-ray laser. It's a free electron X-ray laser. And it gives fully coherent pulses of X-rays, very, very intense, and very, very short. So you can do down to 5 femtoseconds. What we do experimentally is to generate small micron-sized droplets that fall in vacuum. As they fall in vacuum, they cool through evaporation. And they cool very rapidly. They are hit by one of these pulses, and from individual droplets, we get a full diffraction pattern. We can distinguish if we have liquid water, then we have the water ring, the rings, or if we have crystals in the droplet, we get Bragg peaks. As an artist picture of the experiment, so here we would have a 12 micron droplet that falls and is hit by a 3 micron X-ray pulse, and it's generated by a machine which is 1 kilometer long, so this is really shooting with precision. Here's the data. So here's the travel time in vacuum in milliseconds. Here's the temperatures we achieve. Here's the temperature of homogeneous nucleation. And we do go below that down to 227 Kelvin. Here's the fraction of shots that contain ice, respectively water. So we see no ice crystal until we are well below the temperature of homogeneous nucleation. But even at 227 Kelvin, we still have a fraction of the order of a few hundred droplets that have remained liquid at 227 Kelvin. So what can we extract from this? Well, first of all, we need to verify the model. What we have at the higher temperatures, the measurements can be done at the synchrotron, where we can measure the temperature. At the lower temperatures for the droplets, we need to use the Knudsen evaporative cooling model to derive the temperatures. We have a very good overlap between the directly measured temperatures and the Knudsen model in this region, but down here we turn to molecular dynamics simulations to verify the model. So what we do is we simulate a water droplet. Every once in a while, water molecules evaporate from the droplet. In the simulation, we can measure the temperature. And that's a green curve here. Now, to apply the Knudsen evaporative model, we only need thermodynamic quantities. These we can define from the simulation for this particular model. And then when we mathematically model, use these quantities in the model, we have a very good fit. So the data that we're going to look at will be the structure factor. So this will be the normal structure factor measured out to 16 inverse Ångström. But the detector that we have can only cover this range. So this is what we will look at, these two first peaks. Here is the full temperature series. So in this region, at the higher temperatures, we have synchrotron data where we can measure the temperature. Here we have the droplets, and here we have an overlapping region where we have data both from droplets and from the synchrotron. So we have a very good overlap. We have a continuous development of the peaks. So they become sharper and sharper, and they separate from each other. So these two peaks we call S1 and S2. We can plot their position as function of temperature. And we have a continuous development of the liquid structure towards that of low-density amorphous ice. We want to characterize, we want to extract more information from the experimental data. So we want to be able to say something about the tetrahedrality. We need some parameter, and what we will use is the height of the second shell, which we will call G2. Here are experimentally derived pair correlation functions for high-density liquid and low-density liquid. This is from neutron diffraction data by Ritchie and Soper. So the high-density liquid is characterized by a collapse of the second shell, and molecules also from the first shell have moved into the interstitial region. There's very little contribution here. Now this position corresponds to the distance between the nearest neighbors to this molecule. We can take this from the simulations. From the simulations we can derive the pair correlation function. From the pair correlation function we can calculate the split between the S1 and S2 peaks. And this gives us a calibration curve that we can apply to the experimental data to derive a G2 parameter from experiment. And this is what we find. So here's the experimental data. Here's TIP4P 2005, which underestimates the accelerated transformation that we see in the experiment towards a tetrahedral liquid. Up here we have low-density amorphous ice, and it goes towards a much more tetrahedral liquid. Now, I say towards a tetrahedral liquid. Well, people normally speak of ambient water as tetrahedral. Here's the pair correlation function for ambient water. Here's the pair correlation function for low-density amorphous ice. And here is TIP4P 2005. It's a simulation. at 220 Kelvin, and 220 Kelvin is where we have to go in the simulation to correspond to the G2 of the experiment. So, what we have now is we've actually gone down to where the rhythm line should be, and where some models predict that strong things would happen. We see a continuous change in the structure, in the tetrahedrality. It's accelerated when we come close to the temperature homogeneous nucleation. It's much more dramatic than we see from the simulations. And our picture here is in terms of two normal liquids. We have, at high temperatures, a pure, high-density liquid, which behaves perfectly like a normal liquid. So cooling gives an increase in density. At very low temperatures, again, we have a liquid that behaves like a normal liquid, a low-density liquid. But the anomalous behavior occurs in the transition between these two. And that's where the anomaly is. It's a very simple picture. So, it all favors this. I don't have much time. You've seen this picture before. So let me just say something about correlation length, since that was brought up. From the small angle X-ray scattering data, we can extract an anomalous component. Now, what we do here, since we're not focusing solely on the extreme small Q region, but we also go up so we can see the tail of the first peak in the structure factor. This means that we can fit a normal component and an anomalous component. So we can extract the correlation length according to Ornstein-Zernike theory. Here are the data for H2O, for D2O, and for a solution of 1 molar solution of sodium chloride. We can fit an apparent power law to the correlation length. And where we use the temperature 228 Kelvin, similar to the isothermal compressibility and CP. So it seems that even in the correlation lengths we have a critical behavior. But also that for D2O we would be closer than for H2O. And the reason for this is that the hydrogen bond strength for D2O is enhanced over that of H2O. In fact, for a mixture of HDO and D2O, for instance, we would see, and we see this experimentally from X-ray emission spectroscopy, we see HDO more preferentially in the high-density liquid rather than in the low-density liquid phase. And we can discuss that afterwards. Now, the other aspect here is that the correlation lengths are very small. They're of the order 2 to 3 angstrom, so how can that be important at all? Well, one has to remember that in Ornstein-Zernike's theory, what one looks at is the first term in the asymptotic expansion going to small q. So the correlation length in real space corresponds to the asymptotic behavior at large R. And that, oh, I'm sorry, let me go here. And that corresponds to this exponential decay. Now, to make sure that we are looking at the right thing, we have now simulated the liquid gas critical point. Even here the correlation length is small, 5.9 angstrom. but we have a very good description of the asymptotic behavior of the pair correlation function, as Orstad-Zernike theory would say. So what does this correlation length mean, then, 5.9 angstrom? Well, if we look at the simulation box here, and this is now 100 angstrom, so this is to scale, we see that 5.9